Okay. All right, so just before we took a break, I talked about the different dynamic ranges of features, and if you don't do something to that data, it's going to cause a lot of problems when you're dealing with graded descent. You'll actually take a look at some examples in the lab that talk about this. All right. So what people normally do is before you start training your model, you do what's known as normalizing each feature. So what you're doing is for all of your training examples that you have, you take a look at each feature, and for every example, you transform each feature of each example so that it follows a certain guideline. So the reason why you do this is because it allows for the dynamic range of every single feature to be pretty much within the same dynamic range, and that way it allows for the algorithm to converge much faster. Okay, so one way is to transform each feature so that in your training set, each column exhibits what's known as zero mean unit variance. It's, mean and variance is stuff that you've seen in probability. All right, but I won't ask you to compute it. You're going to use MATLAB to do that. Okay, so basically for each instance that you have in your training set, in your training data set, so in the training set, okay, what you're going to do is you're first going to compute the mean and the standard deviation of that particular feature. So for example, if you have 10 examples, what you want to do is for the first feature, you calculate what the average of the first feature would be and also the standard deviation of that feature. Once you do that, you go through every single example that you have and you do the following operation. So you take that feature, right, that you're looking at for the particular row in the matrix, you subtract by the mean and divide by the standard deviation. So this transformation is done so that when you compute the average of this particular column, it becomes 0, and the standard deviation of that column becomes 1. It's what's known as zero mean unit variance, because that's what's actually going to happen. Okay? So for each feature in an instance x sub k, all right, you're going to first compute the mean of that feature, the standard deviation of that feature, and then for every single example that you have in your training set for that particular feature, you subtract by the mean and then divide by the standard deviation. So once you transform every single one of your points for each feature to follow this particular transformation, then your data will more or less have the same, relatively the same dynamic range. So you train your prediction model using this transformed data, and finally you'll have an output. You'll have the output parameters that are based on those normalized parameters. But if you want to actually start using it to predict new values, you have to apply the same transformation that you did from the training to your new instances. So what you have to do is you have to make sure that you remember what the mean and standard deviation is for every single feature. So in the lab, there's code that I wrote where when you submit a data matrix, the output will give you the normalized feature matrices as well as the mean and standard deviation for every single column. The reason why you need this is because for every new instance that's coming in, you have to take that new instance and you have to subtract with the mean of every feature and divide by the standard deviation of every feature. So you're doing this for the training data set, the mean and standard deviation. And once you do that, then you apply your prediction model like that. Okay? So you normalize, you train the model using these new features, all right? And then you also have to remember what the mean and standard deviation is for each feature. Okay? Once you do that, now you take a new instance, right? So it's something that you've never seen before, or you have seen before, but you want to compare what the accuracy is. And then you take your new instance, and then you take every feature and subtract it by its corresponding mean, divided by its corresponding standard deviation, and that would be the new feature that you use to submit it to your prediction model. All right, so that's what you have to do. It's not, it's not so bad. The lab has more details about that. Okay. So that's about feature normalization. So what about the learning rate? Okay, so how do we choose the best learning rate? For convergence. You may have noticed that in the past, we've just specified one value of alpha, the learning rate. You set it at 0.1 and then you let it go. Right? But depending on which problem that you're dealing with and depending on the dynamic range of your data, setting it as, let's say, 0.1 every single time may not work, because sometimes it might converge, sometimes it might diverge. So how exactly do you figure out the best one to choose? Well, there is no best one to choose. Okay, all you have to do is you just have to try a bunch of different ones and then see how it works. But I'll give you some guidelines to figure out why, or figure out how to actually choose the best one. Okay, so, all right. First, sorry, first. We can look at the cost function. Okay? If you choose a right learning rate, and then if you take a look at the cost, if it starts decreasing over time, over the number of iterations, then you probably chose a good learning rate. You want to make sure that the cost decreases at every single iteration. If it increases or if it kind of oscillates back and forth, then you didn't choose a good one. You want to decrease that learning parameter in order so it doesn't overstep. All right, so first we can look at the cost function. If it decreases at each iteration, then the learning rate is good. Well, how good it is, it depends. The learning rate is a correct one. Right, so something like this. So for example, if I had a plot like this, and this is my cost, right? And this is the number of iterations. It should look something like this, right? It decreases over time. Right, so for example, this would be 100, this could be 200, and so on and so forth. Okay? So this should decrease at every iteration. Okay? So another way to check to see if it converges, I didn't actually do this in the code, but a good way to make gradient descent stop is if the cost between two iterations is less than the difference between is less than a certain amount. So a good way to check if algorithm converges is if the cost difference between two iterations is less than a threshold, than some threshold. No, for example, something like 10 to the minus 3, I guess. So the lab that I wrote, it expects you to specify, a total number of iterations if it's 100, 200, and so on, but I actually didn't implement it so that it stops automatically. So this is a good way to, maybe get the algorithm to stop on its own. So you can take the difference, between successive costs, and then you can see if the difference is less than a certain threshold, and if it is, then you stop. So that way you don't have to manually specify how many iterations you want. You can just get it to stop on its own. Okay. All right. So if cost increases or oscillates at each iteration, okay, then the alpha is wrong. Choose another one. Okay, so let's say you land with the wrong one. Let's say you chose an alpha of 1 and then it blows up for you. So what do? You probably want to decrease it, but what I usually do is I have a range of learning rates I test, like say 0.1, 0.2, and so on. I've got a vector of different learning rates, and then what I do is I just loop through them all and I see which one of them, has the converges. And then once you figure out the ones that converge, see what the final cost would be at the very end. So then you choose the learning rate that gives you the lowest cost. So first have a wide range of alpha values that, and then you pinpoint the ones that converge. Once you figure out the ones that converge, choose the one that has the lowest cost, and that's how you stop. Okay, that's what I usually do. So, okay. All right. A strategy that is used to make sure algorithm converges is to try different learning rates. Okay? On a logarithmic scale. Logarithmic scale. Right? So something like, so for example, and then you set a maximum number of iterations. for each scale. It's all going to be the same. Okay? If the algorithm doesn't converge, you move to the next one. Doesn't converge after this many iterations. Try the next one. Okay? So usually I do something like this. So usually I start off with 0.001 and then I scale this by a factor of 3 and then I scale this by a factor of 10. So you can kind of see it's sort of logarithmic, but not exactly. And so on. Okay? So I usually do this. So the difference between two values would be 3 times, and then the difference between every other one would be 10 times. So that's what I usually do, and the lab actually talks about this more. So I start off with a very small learning rate, like 0.001, see if the algorithm converges, or see if the cost function either increases or decreases, and then try the next one. So 0.03, and then I go 0.01, 0.03, and then 0.1, 0.3, and I keep trying a whole bunch of different values, and then I see what the cost function looks like, and then I choose the one that has the lowest cost, and then I'll end up just choosing those. All right? So go through and figure out which has the lowest cost. So the lab actually touches up on that, the lowest cost, and choose that learning rate. So there's many different learning rates that will allow the algorithm to converge, but you want to choose the one that has the lowest cost. All right? Okay, so that's one way to choose. So you have feature normalization that will allow the algorithm to converge, and you also have different learning rates you can choose. So the combination of those two should allow you to get the algorithm to converge. So that in the lab it talks about that. Yes?
Did you look at how long it takes to convert this over?
Yes. You also see what you can do is you can take a look at the cost function as well. So if you see that it converges very quickly, that's also a factor as well. Because sometimes you'll see the curve that kind of like dips down and then kind of plateaus, and other times it might take a little longer to converge. The cost function will tell you that. So you can actually take a look at the shape and see how quickly it converges. So if you see that one, it takes like a little dip immediately and then it's flat, and that's probably a good indication that it converged quickly. Or if one, it takes like a very long time, like it's kind of like a smooth slope, then that's probably not there's probably other ones that you can choose. So in the end, what you do is you take a look not only at the final cost value, but as well as the shape of the curve. So if you probably want to choose one that the shape is quite sharp because it takes a very short amount of time to converge, and as well as the cost being very low. Okay? All right. Okay, so let me. I'm going to talk about polynomial regression. I'm going to save the large scale stuff for next class because I'm actually running out of time, unfortunately, and that'll be a good thing to take a look at. Okay, so so let's see here. So last topic, we're going to talk about polynomial regression. Okay, polynomial regression. Okay, so it is possible to take, for example, the one feature, if it's, tumor size or housing price or so on, and then using just that feature, using just, a straight line of best fit is probably not, a good indication of that it's going to be very accurate. So what people usually do is that they introduce more features. So for example, you might want to fit a parabola through the points, or like a qubit function through the points. You're able to do that with linear regression here. You just have to add more features. All right? So we can still use gradient descent. Yeah, I'll talk about the online learning stuff next class. I don't have time for it, unfortunately. So to fit lines of best fit of any shape, right? So you can make it a quadratic, you can make it cubic, and so on. All right? Okay? So all you have to do is just take one feature and then apply the correct transformation to it. So not only do you have just a single feature, you might want to add, you might want to make it quadratic. So you take the feature and square it or cube it, depending on whatever feature you want. All right? So simply take one feature and apply the correct transformation to it. So usually a quadratic might look like this. So your prediction model may look like, so theta 0 plus theta 1, x plus theta 2x squared, right? Or a cubic, you want to introduce another feature, which has the cube term. So theta 0 plus theta 1 plus theta 2x and so on, all right? So this is good if you just have one feature and if you want to introduce more, degrees of freedom in order to be able to predict the right line. So this is feature number 1, right? Right, it's just the x term. This here is feature number 2. It's just x squared. And then finally, this is feature number 3, all right? It's just cubic. Okay. All right. So here's a quick example. Actually, I'll start with online learning as quickly as I can, then I'll finish off in the next class. So something like this, I guess. Maybe something like this. Might look something like this. I don't know. So here's a bunch of stuff, right? So this is x and then this is y. So let's say we have this, right? So obviously, if you try to put a line of best fit, it's probably not gonna predict well. So this is using just one feature, right? But maybe you want to fit maybe a cubic through it. So maybe it'll look like this, for example. Maybe this probably is a better indication of a good fit, right? So this is for cubic, right? So clearly this data is nonlinear. So if you try to fit a linear straight line through this data, it's probably not going to give you the best results, right? So clearly this data is nonlinear. Okay? So all you have to do is you just take the one feature and then you just add more features to it in order to get good results. So we take just one feature and add more features. To get a better fit. Yeah. Yes, question.
Is there a particular reference to which one you're going to be using or squaring?
Well, honestly, you just have to try a bunch of different ones and see what the cost function looks like, and then you choose the model that best gives you, like, that minimizes the best, that minimizes the cost function the best. So there's just a bunch to try. But next class, we're going to talk about adding and possibly infinite number of features. And that's okay because you'll use a concept which is called regularization, where you can add as many features as you want and it should be okay. So, but yeah, in general, it's just experimentation. You try cubic, see if that minimizes the cost function. Maybe you try quadratic, see if that minimizes. So you're just choosing the one that will give you the smallest cost function, right? So let's see here. For each additional. Okay, so what's a problem here is that every time you decide to add a feature, whether you take a feature and then you square it or cube it, what's going to happen is that the dynamic range for that feature will start to increase exponentially. So for example, if I had a feature of 40, if I introduce the cubic term, that's going to be 40 cubed, right, which is 202.56 million. So every time you introduce a feature of a higher degree, that dynamic range is going to increase a lot more. So if you decide to do polynomial regression, you got to make sure you normalize your features before you train your model, because that dynamic range is so high as you start increasing the power that the gradient descent will actually be very bad unless you feature normalize. All right, so for each additional feature, the dynamic range changes, or the dynamic range gets worse, or it varies more. The dynamic range increases exponentially. Exponentially. All right? So what's going to happen is, for example, let's say I had, let's say x was between 0 to 1,000, all right? If I decide to square each term, it's going to increase. This will go from 0 to a million. Right. If I decide to cube everything, it's going to go from 0 to 10 to the 9. So it's important that you feature normalize everything before you decide to train your model. Okay, so feature normalize before training. Okay, so in general, the prediction model is just a sum of polynomials that are weighted by a certain amount. All right, so it's just the summation from 1, well, 0. We can try 0. Sorry. Theta I x to the power I. All right, which is just theta 0 plus theta 1x plus theta 2x squared and so on. All right? And the data matrix is going to look like this. All right, so you have a bunch of 1s here, right? And then you have first example, second example, on to the last example. And then you have the first example squared, second example squared, right? Keep going, squared, and then you keep going to the end. And there's, sorry, this is n, sorry. We'll make that powers instead of examples. Okay, that's good. And this is, in mathematical terms, this matrix is what's known as the Vandermonde matrix. If you take a look at some linear algebra or calculus textbooks, this is what is known as a Vandermonde matrix. And then you got to make sure that you feature normalize before you use this. All right, so feature normalize. Okay, so that's how you do polynomial regression. So you just create a data matrix where each column is that particular feature to the power of whatever you want. So square, cube, to the power 4, whatever. So if you had, for example, in the lab, it's to the power of 8. So you have a column of 1s, and then you have x to the power 1, x to the power 2, all the way up to x to the power 8. So you have a whatever, m by 9 matrix. Make sure you feature normalize each column. So you extract the mean and standard deviation of each column. Train your model, and then when you use it to predict new instances, use the mean and standard deviation to normalize, and then use the prediction model to predict your values. Okay? And that's it for polynomial regression. Any questions here? Yes? Yeah?
There's only one, is it just one feature?
Just one. And then what you could do is you can have a combination of different features. Let's say you had 4 features, for example. You can make a 5th column that would take the first feature squared. Or you take the second feature and multiply it to the power of 3. So it totally depends on what you want. You can just do it for this particular case, it's just one feature, but you can introduce other features that are nonlinear. Like you can take the third feature, add it to a power 3, and so on. Like you could add additional features by just taking one of them and applying a power operation to it. It's up to you. This example here is just one feature, and that's what's covered in the lab. But in general, you can take your data matrix and you can introduce other features by just taking one and then applying a power operation to it if you want. Sometimes, for example, in housing prices, a feature would be like you would take, I guess, the length times width, or you would take hectares, or you would take one feature and you would multiply it by another feature, and that would be another feature that you introduce in your data matrix. So you're able to combine them as well. But this is just for one feature, but in general, you can apply it to any feature in the data matrix you want, and just add another column that will apply the transformation you want. Okay? All right. Okay, let me just do a quick intro to what I want to talk about next week, and then we'll convene here. I will end a little early, though, because I don't have time to do this. But, okay, I just want to give you a little taste of what we're going to talk about next week. So let's talk about large-scale machine learning. Especially if you go work in the industry in terms of big data and data analytics, the amount of data that we're accumulating in terms of the amount of processing power that we have is so very improportional. Like every time you take a photo or every time you save documents to your computer, the rate that we're getting and consuming knowledge is very vast, and we don't have enough of the technological power to be able to process everything all at once. All right? So in practice, the amount of data, I'll try to cover as much as I can, and then I'll end it, because I won't be able to cover this all today. The amount of data collected of different domains is vast. is huge or vast. Okay? Mainly because, back then, maybe 15 or 20 years ago, buying a 256 megabyte USB key cost you like $50. It was ridiculous. And now you go to the store, you buy a 2 terabyte, or it's not 2 terabyte, like a 32 gigabyte USB for 30 or $40. It's ridiculous, the amount of, how storage has matured and how cheap it is, right? So storage is cheaper, okay? And the internet is affordable and fast, right? Because you can download stuff at remarkable speeds. Okay? So usually when you collect training sets for any practical application, it's not limited to just a few hundred training examples. It's usually within tens of thousands or millions, especially if you're dealing with anything medically related, or if you're dealing with anything with quantitative trading, or if you're on Wall Street, or you're dealing with big data and doing predictive modeling. The training examples that you get are usually within the millions, all right? So let's see here, sorry. Usually, training examples collected are in the millions. I would have loved to do something large scale for this class, but the department doesn't have resources for it, so unfortunately I had to can that idea. But maybe in the future. All right. So recall how gradient descent works. I'll just give you a little bit of a flavor of what I'm going to talk about, and then I'll end. So recall how gradient descent works. So there's two things you have to take a look at: the cost function, as we talked about before. Actually, not cost function. We'll just talk about the hypothesis, right? It was, theta transpose x, or, and then we had the cost function, right? It was 1 over 2m, and then sum of 1 to m, and then I've lost count how many times I've written this formula. It's crazy. All right? And then you have to repeat. So you update simultaneously. Alpha m, and then okay. And then x, j, i. Okay. Now, if you take a look at this version of the algorithm is called what's known as batch gradient descent. What batch gradient descent means is that you have to sum over every single one of your training examples before you compute an update for one parameter. You have to batch process all the examples at once, and then you make a single update. So this version of the algorithm is known as batch gradient descent. All right? So this version is known as batch gradient descent. Maybe I'll be able to finish this today, who knows, okay? And this thing is that you must sum over all training examples, okay, for a single update. Okay? Now the problem with this is that if you have, let's say, a data set that's in the millions, right? Summing over every single element, every single instance that where you have the training set that's in in the millions it'll probably cost you a lot. Right? You can't put it in a matrix because that matrix of data points is not going to fit in memory. All right? So problem. If data set is large, this will be slow, right? Because you're summing over data, m when it could be a couple of million, and that's going to take you a long time. Okay, so the solution that people usually use is what's known as stochastic gradient descent. And what stochastic gradient descent means is that you only use one training example, and then you update the parameters every single time. So you take a training example, you update the parameters. Then you go to the next training example, you update the parameters. So for each training example that you have, you immediately update the parameters. So you don't have to sum over all of the training examples that you have. You just update the parameters every time you see a new training point. So that's what's called stochastic gradient descent, where you do an update for just one point instead of as many points as you have in your data set. So the solution is one is known as stochastic gradient descent. This will be my last topic, and then I'll stop. Stochastic gradient descent. Okay, so the idea is make an update for each parameter after using one example. So one example, instead of having to sum over m examples. Okay, so the reason why you do this is because you can see the change immediately after you just do the one example. And I'll talk about the advantages and disadvantages of this approach in the next class because I'm running out of time. So you see changes immediately. So I'll just give you what the pseudocode of the algorithm would be, and then we'll stop. Instead of having to sum over all examples. So you're just using one example to do the update rather than several or whatever the size of the data set will be. Okay? So the algorithm is this. Okay? So obviously you initialize, right? So one, initialize parameters, just like you did last time. So usually people just, set them all to 0 for a lack of better choice. Okay? And then what's important is that you have to take your data set and you have to randomly shuffle the data set, because what's happening is that you're not observing all of the behavior all at once for when you're doing batch gradient descent. Because you're doing stochastic, you're only looking at one training example at a time. So it's good to actually shuffle the data set before you do this, so it allows for a faster convergence. It's what is commonly done in practice. So 2, randomly shuffle or reorder, So all you're doing is you're just gonna, take the example, you're just changing the order of how you're seeing the training examples. So randomly shuffle or reorder the data set. Okay? It's usually for faster convergence. I'm almost done. I'm just going to spit this algorithm out for you and then I'll stop. And then 3, it looks like this. So you repeat k times. And k is usually between 1 and 10. So usually k is between 1 and 10. It just depends on experimentation. Then unfortunately, all experimentation is all you have to figure out what the best value is. And then for I equals, so for each training example, 1, 2, all the way up to m. So for each training example that you have, what you're going to do is you're going to compute the update immediately. So, and m is only 1 here, so it's just alpha. And then we have okay, and this is for j equals 0, 1, all the way up to n. Okay, and also x0 is just 1. Wait for the bias term. Okay, so that's pretty much the only difference. So there's an outer loop here, okay? And what this does is that you're basically cycling through the data set a few times, so 1 to 10 times. So this is the iteration, so to speak. For batch gradient descent, you're iterating a certain amount of times. This controls how many times you iterate the algorithm. So controls how many times, how many iterations. Okay, usually between 1 and 10. Okay, and then this handles the data, so handles training examples. Okay, so for each training example that we have, what's going to happen is that you're going to use that training example, you're going to use each feature from that training example, and then you're going to update the parameter that is specific for that feature. So that's what the for I is equal to 1 to m does. So for every training example that you have from 1, 2 up to m, the first training example, you use that to update theta 0 up to theta n. And then you use that for the next training example, which is 2, you update the parameters. So you just So you're cycling from the first up to the last, and then you're updating the parameters that way. And then once you finish the entire data set, then you go back to the beginning and you start again. And then you do it for, between 1 and 10 times. It depends on what the problem is at hand. Okay, so that's what stochastic gradient descent would be. So let me just, let's see here. All right, yep. I'm just gonna write these couple last lines and then I'm gonna stop and then we'll talk about it next time. So, to summarize, your update each parameter after each training example. Okay, and B, cycle through the data set, as I just talked about. Cycle through the data set k times, where k is some number. Okay. Now let me see. Okay. And actually, let me see. Actually, I'm just going to blaze through this. I'm almost done here. Yeah, I'm actually almost done. I'm just going to blaze through it if you don't mind. Sorry. Unless you want me to quit. I've got like 3 more pages. Keep going? I'm almost done, so, all right. Okay. So how do we check for convergence? Okay, how do we check for convergence? Because what's happening here is that when you're calculating the cost for batch gradient descent, what you're doing is you're summing over all training examples, and then you're seeing how much the cost would be to assign, those parameters to that particular data set. So what you have to do for stochastic gradient descent is that what you're doing is you check what the cost is for every 1,000 examples or every 2,000 examples or so. So between the first and 1,000th example, you calculate what the individual cost for that would be. And then you take the average of all those costs, and then you see what the average cost would be. So between every 1,000 examples, compute what the average cost would be for just the one example, and then you see what the convergence looks like. And if it's sort of going down, then you're probably on the right track. Okay? So in batch gradient descent, okay, we calculate the cost after looking at all examples. Okay? Okay, for stochastic gradient descent, what the usual practice is that for every P examples, so P is usually between 1,000 to 2,000, so P is usually somewhere around that neighborhood, all right? And then what you're going to do is calculate the individual cost of each example. So what you're doing is you're basically calculating okay, so you're calculating this for each training example. Okay, and then what you're going to do is you're going to take a look at each one of them, and then you're going to find the average over 1,000. All right, so average the P costs to get a final measure. All right. So usually it looks like this. So for example, if your plot might look like this, and what's going to happen is this is the number of iterations. All right, and then it might look like this. Yeah, I'll skip the map reduce part. I don't need that. Okay. Yeah, this would be the last thing I talk about. Okay, so it might look like this. So this is when k is equal to 0, right? This is from 1 to 1,000. This is 1,001 to 2,000, and this is 2,000, and so on. So on, and then this is when k is equal to 1. No, sorry, this is 1. And then you repeat the same stuff. Okay, so it might look something like this, because what's happening is that you're not looking at the entire data set, you're only looking at chunks. So what will happen is that the cost function might oscillate a little bit, but As long as the general direction is going downwards, then you should be okay. So it looks something like this. It might look something like this. Something like this. Something like that, I guess, as long as it's going down. All right, so cost oscillates, but tends to go down. Okay, so if J of theta is oscillating, I'll show one more contour plot, and that's it. I've skipped a bunch of stuff, but it's okay. I just want to finish this once and for all. If theta is oscillating or increasing at every iteration, choose different learning rate. Okay, so it might look something like that. Okay, and this is my final slide for you. So I just want to see, sorry, go back up. Where is it? So let me show you a contour plot. Here we go. Okay. So if you remember, batch gradient descent kind of looked like this. So this is our initial point. This is our contour plot. This is an initial point. Okay. And then, you know, batch gradient descent might look something like this. You kind of it slowly goes towards the minimum. So here, this is what batch gradient descent might look like. All right. And then stochastic gradient descent is going to change a little because what you're doing is you're not looking at every single example. You're looking at chunks of data. So what's going to happen is that it might oscillate to look like this. So you have like this. It might look something like this. It'll eventually go around the minimum somewhere, but it's going to oscillate around the minimum. So this is stochastic. So with batch gradient descent, you had the luxury of being able to look over every single training example to figure out whether or not each training example fits those parameters nicely. But with stochastic gradient descent, you're only looking at one example at a time. So there might be chunks of data where it might fit very nicely, but then those parameters might not fit with the other chunks of parameters, which is why the cost oscillates, because you're actually looking at chunks instead of the whole entire data set. All right? So stochastic tends to oscillate around the minimum, around the best parameters. Okay. All right, and that's about it. So the main application why you'd want to use stochastic gradient descent is, let's say you're an online merchant, right? And you want to be able to predict housing prices. So what'll happen is, let's say you've got a huge database of numbers where you have, square footage and the number of bedrooms and so on. And let's say your data set was in the millions. And let's say someone else comes by your website and puts in some new data into your website. Let's say they put in one training point. If you were to use batch gradient descent, you would have to retrain the algorithm using every single data point. So you'd have to train over 2,000,001 points. And that's not really good, right? With stochastic gradient descent, what you can do is that you just have to retrain your parameters, but just using that single parameter. Because all you're doing is you're updating it based on just one example, right? So instead of training over millions of points again, you just have to take that one example, apply stochastic gradient descent, and then you just update your parameters like that. So it's good for what's known as online learning, which is able to relearn your parameters just by using just one example point, rather than having to sum over every single point again if you just introduce a single data point. Okay? And that's all I have to say. So thanks for being very patient. So next week we're going to do something completely different. We're going to talk about classification, which is another cool thing about machine learning. Okay? Thanks.